Hi, my name is Eric DeWitt. I'm a researcher at the Champalimaud Foundation here in Lisbon, Portugal, and I'm here to talk to you today about Bayesian inference and decisions. But first, a little bit about me. I'm a computational and experimental neuroscientist. I work with a fabulous group of people in something called the International Brain Lab, which has brought together more than 20 experimental and theoretical laboratories throughout the world to study mouse decision making. And now I'm going to talk to you about why we should care about the Bayesian approach. So, what is the Bayesian approach? The Bayesian approach describes a philosophy and a rule, and we'll get to the rule in a minute. But the philosophy is there is uncertainty in the world that we need to represent. And this uncertainty could be intrinsic in the world. You can think of things like quantum uncertainty, or it could just be that there's always uncertainty in trying to estimate something where we have imperfect measurements. So think about the fact that, when we do science, we have to experiment using devices that measure things, and those devices may have noise in them. Or your eyes or your ears. They're not perfectly able to capture light or sound, though they're very good, and so there's always uncertainty. When we ask a question, we want to know how likely the question is to be true, and we want to know how confident we are in the answer. So if we represent uncertainty, then we can answer these kinds of questions. And the final bit of the philosophy is we should always be trying to use all the information you have to make a decision. Let's take a look at this simple graphical model. In blue, you can see something that we're calling the world state. The state of the world is true, but hidden from us. We're going to call it S through the next few days. But we can take measurements from that world here in red. We're going to call them M for the next couple of days. And these measurements tell us something about the state of the world. And these are random variables. So if you've studied probability theory, you know what they're going to be. And what we want to ask is, what is the probability distribution over this hidden state, this thing that we actually care about? And so as I said, we're always going to face this uncertainty, and it doesn't really matter whether we think about this as noise in the world or noise in our cognitive system. As scientists, we take measurements about hidden things in the world, and as brains, we take measurements about hidden things in the world. So, the rule. Bayes' rule is very simple. It says, let's imagine we want to know the distribution, the probability of a hidden state, given some measurement we've taken. We can call this our beliefs about the hidden state, a distribution of probabilities of the hidden state being some value. In order to calculate that, what we're going to do is do a clever thing and invert this question, what is the probability of the hidden state given the measurement, and we're going to turn it around, and we're going to ask what is the probability of seeing this measurement given the probabilities of the hidden state, and then given something we're going to call the prior probabilities of the hidden state. And then we need to normalize this so that it's a probability distribution. So we ask, what's the probability of the measurement overall? So importantly here, there are some really key elements to this formula. There's the prior. The prior describes your knowledge about the hidden state. There's the likelihood, a conditional probability that tells us how much information we gain when we take a measurement from that hidden state. And there's the outcome, the posterior distribution, which describes our beliefs after gaining information from a measurement. And then we're going to normalize by just averaging out all of the possible measurements we could have seen. All of our estimates are decisions. And this is something that's a little bit deep. When we think about Bayesian inference, or inference in general over probabilities, often we're asked, well, what is the mean? What is the mode? What is the most likely outcome? Those are specific estimates, point estimates that we take when we make a decision about how we're going to treat some random variable, some distribution of probabilities. So we can think of them as decisions. So we're going to combine thinking about estimates, judgments, and decisions, and we're going to bring it into this Bayesian framework. So whenever we want to take an action or make a decision or an estimate, and we have uncertainty, we have to ask what is our expected gain or expected loss from taking this action given our beliefs. In general, we call gains or losses the utility of the action, given the true, but of course hidden to us, state of the world. So, a utility function defines this in a formal way, and if we want to actually know what our expected utility is, that is the utility for a possible true hidden state of the world, S, and an action we take, which is some guess about where in that world we really are, we then find out what the value is there, but if we want to do this over a distribution, we're going to have to integrate if it's a continuous distribution, or we're going to have to sum if it's a binary or a categorical distribution. So, over the next days, we're going to use this framework and we're going to think about it. So we're going to start with this very simple basic Bayes. We have a single hidden state of the world and we're going to take a measurement from that. We're going to think about taking measurements from that. Then we're going to move to a more complicated world, a world where that hidden state can change over time. These are called hidden Markov models, and you're going to learn more about them in the next day. And then we're going to incorporate the actions that we take based on our beliefs, which can also affect the state of the world. And we're going to think about what happens when we know how those actions might affect the state of the world. And we're going to look at Markov decision processes and optimal control. And then finally, we're going to finish the week thinking about how we could learn about these kinds of things, though we'll actually not really get to the hidden state component. So, Bayesian approach as a tool. We are asking statistical questions about our experimental data. You've already seen in model fitting maximum likelihood estimation, which is in fact that likelihood term that we were just looking at. And we can also think of as regularization, which you've also seen, as a set of priors. That is a set of prior knowledge about where we think the parameters are, how sparse they are. So we can apply many of the concepts that we need to do for our normal statistical inference using these Bayesian tools. And I'm going to point out here that there are often equivalent or at least compatible alternatives in something called the frequentists' view of the world. The frequentist view of the world we're not going to really talk about today, but it's where we're going to consider probabilities as really descriptions of hypotheses and tests on those hypotheses. So when we formalize scientific beliefs about those kinds of hypotheses over our data, we can still use Bayes' rule. We're just going to have to think about what the possible hypotheses are, what our prior knowledge is, and what information may inform us about one or another of those hypotheses. Finally, we can use this to define optimal inference or optimal decisions, that is using all of the available information, and we can compare this to behavior or the brain. This is a normative approach. And the Bayesian approach to modeling behavior in the brain, we can think of this as something that a human, an artificial agent, or an animal has to do every day because they have beliefs about the world and they're going to use measurements from their sensory system to guide their behavior. These are Y models, and they allow us to precisely describe our knowledge, the information we have, the uncertainty we have, and then we can ask, what can you know? It forces us to define goals precisely, to ask, what should you do? This is the normative component when you add utility, gains or losses. And they force us to provide a complete description of the uncertainty we have. So we can think about how confident are we and how confident could we be. And we can compare these normative models to data to test our Y explanations to see if they're appropriate.